right, everybody, let's get started. Good afternoon, everyone. Welcome to the North Carolina Museum of Natural Sciences. Thanks for coming out to the Daily Planet Theater today. My name is Chris. I'm curator for the Daily Planet, and I'm your host every week for our Lunchtime Discovery series that we have every Wednesday at noon in this space. You get the chance to meet scientists and professionals working in science and nature and conservation and wildlife and all kinds of great, incredible fields. We bring them here into the Daily Planet Theater. They give a talk, we ask questions, and we have a great discussion about what's going on in science all over the world. But most of the time, we're talking about stuff that's happening right here in our own backyards in North Carolina. This series is put on, we host it here inside the museum, but our guest speakers are invited and set up by the Office of Environmental Education within the Department of Environmental Quality. So we have a great big team that works together very hard to pull these events together every week. And every week we broadcast the show live to the web. So if you've missed some, want to go back and learn new stuff from other experts, you can check out the archive. We can connect you with the link there. And hi to anyone who's watching online right now. We're live on the internet. So I'm glad that everybody has tuned in. Today's expert didn't have to go very far to get here. Well, actually, he just got back from a conference in Hawaii, so that was kind of far to get here. But his office is on the third floor of this building. Dr. Patrick Treuthardt is the assistant head of the Astronomy and Astrophysics Research Lab here at the museum, and he's been working on this pretty cool project where anybody and everybody can help him study galaxies. That's pretty fun, right? At least it sounds cool. I've seen the format, the way that people can help, and the types of studies that he's working on. Heard a little bit about it before, because his office isn't very far from mine. So I think you're going to enjoy hearing about it today, too. Put your hands together and welcome Dr. Treuthardt to the stage.
All right, thank you. So sorry about the title. It's a little long. I actually cut a word out. But it's basically what I'm going to be talking about is a citizen science project that I've developed with volunteers and interns here at the museum to help find a specific type of black hole in galaxies. So before I actually get into that, let me talk about black holes in general, because I have a feeling a lot of people don't know how they form, what they really are, things like that. So we'll start out really basically. So stars, when they reach the end of their lives, they can go in different directions. So when a star is born, basically what happens is it starts burning fuel. It starts converting hydrogen to helium, helium to heavier elements, and so on. And eventually, and stars, when they're formed, they're formed at different masses. So our sun is basically a small star. You know, it's 1 times the mass of the sun, right? So we're gonna measure everything relative to the mass of the sun. So the sun is just kind of an average star. It's going to live for about 9 billion years. We're at about 4.5 billion years right now. There's smaller stars that are red dwarfs, and those stars, they'll just eventually burn out like billions of years from now. They'll just burn out. They'll just kind of fade away and stop converting hydrogen to helium, for instance. But things get really interesting when you find stars that are more than 8 solar masses, more than 8 times the mass of the sun. When they reach the end of their lives, their core collapses. The core of the star collapses and becomes a really dense object. So more than 8 times the mass of the sun, they can become something called neutron stars. More than 20 times the mass of the sun, that's when you can start to get black holes. That core will collapse, and it'll actually form a black hole. So what you're seeing here, so the 8 solar mass star that I show next to the sun right there, that's about the size of 8 times the mass of the sun. The next star that says greater than 20 solar masses, that's actually about 100 solar masses. So that's actually much, much larger than the sun. So what ends up happening is the center of the star, it uses up all its fuel. So it's converting hydrogen to helium and then helium to much more heavier elements and so on. And so eventually the center of the star becomes very, very dense. And the gravity from all that dense material in the center basically can't support itself anymore with all the radiation that's coming out of it, and it'll just collapse inward. And can become, one of 3 different types of objects. It can either become something called a white dwarf, which is basically 1 to 1.5 times the mass of the sun, or a neutron star, which is about 1.5 to like 2 times the mass of the sun, or a black hole, which is, I'm sorry, from 1.5 to about 3.5 times the mass of the sun, and then, or if it's more than 3. So that's what we're interested in, is these black holes. So this is just an animation showing you like an artist rendition of how a black hole would form from a star. And so what you're seeing is the central core collapses, and then it expels a bunch of energy, which creates that supernova that you. Okay, so again, sorry about all this text, but these diagrams are actually kind of helpful. So ignore all the text. I'm just going to talk about the pictures. So on the left side there, what you're seeing is this is what's happening in the central part of a white dwarf. And what you see, if you guys remember chemistry, right? You have a nucleus of an atom, and then you have electrons in orbits around them, right? So what happens with a white dwarf is it's so dense, and there's so much pressure in the center that the electrons are actually pushed right up against the nucleus of the atoms. So even though they want to be further away from the nucleus, they're actually pushed right up against it, and they're just smashed into the nucleus of the atom. But there's not enough mass above it, there's not enough gravity to really push it any further. So the force of the electrons not wanting to be really close to the nucleus of the atom is counteracting the force of gravity inward. So there's a balance in forces right there. But if there's much more mass than that, those electrons are actually pushed into the nucleus of the atom. So they're actually pushed into the protons. And so an electron is negative, a proton is positive. So when you merge those two things together, you end up with neutrons. And so now you have a bunch of neutrons all smashed together, and they obviously don't want to go any further. It's because neutrons don't want to be on top of each other. So now you have something called a neutron star, which is that middle ground. But if there's much more mass than that, those neutrons, the gravity can actually force those neutrons into each other. And when that happens, there's actually no other known force outward that can stop that collapse of all that mass. And that's how we get a black hole. So all that mass collapses and keeps collapsing and never stops collapsing because there's no known force to stop it. And that's how you get a black hole. So that central point where all that mass is compressed into, that's the black hole. Okay? So this is very generally how black holes form. Okay, so when we talk about black holes, one of the interesting things we want to talk about is the escape velocity. So if you're standing here on Earth, obviously if you take a ball and you throw it upwards, right, it's going to come back down. And that's because gravity takes a hold of that ball and then pulls it back down toward the Earth. So if you throw it harder, you give it more velocity upward, it'll travel a little bit further, but then it still comes back down. But if you throw the ball hard enough, if you give it enough velocity, it can actually escape the gravity of the Earth and never come back, right? So if you start out further away from the Earth, so if you're in the International Space Station, for instance, and you toss the same ball, because you're further away from the source of gravity, further away from the mass of the Earth, you toss this ball, you don't have to give it a lot of velocity before it completely escapes the gravity of the Earth, because you're further away from the mass, right? So the same thing is true with black holes. The closer you get to that black hole, the closer you get to that point where all that mass is, the higher the escape velocity becomes, okay? So this is just showing you how it works on Earth, right? So if you give an object a little bit of velocity, it's not going to be able to escape the Earth. It's just going to travel a little bit and then fall back toward the Earth. You give it a little bit more, it's going to go a little further. If you give it just enough, it can actually go in orbit around the Earth. But if you give it more than what it needs, it'll actually escape the Earth. Okay, so if you're starting at that point on the Earth there, for instance. So the difference is, okay, and again, I apologize, there's an equation here. But everything on here you don't have to worry about, okay? So most of what you're seeing here are all just constant numbers, so they're just numbers. The only thing you have to pay attention to is the r and the m. The r is the radius where the escape velocity is equal to the speed of light. Okay, so what you see is the greater the mass of the black hole, the greater the radius where the escape velocity is equal to the speed of light. Okay, so what that means is if you're that distance away from the black hole, from that central point, the escape velocity is equal to the speed of light. And nothing can move faster than the speed of light. Speed of light is the fastest thing in the universe. Okay, so if you're inside that radius, if you're inside that distance, light cannot escape that black hole anymore. The escape velocity is higher than the speed of light, and light is the fastest that anything can go. If you're outside of that, things can still escape. So light beams can still escape away from that black hole. So this is when we talk about the size of a black hole, we talk about this horizon. We call this the event horizon. This is where the escape velocity is equal to the speed of light. Oops. So when we talk about the size of black holes, it's really the radius where the escape velocity is equal to the speed of light. So the more massive a black hole is, the bigger that radius is. So here, this little diagram I'm showing is just showing you different mass black holes. So these are what we call supermassive black holes. So there's a 3 million mass supermassive black hole on there, and you can see it's kind of tiny on the bottom. Let me actually point to it, although people online probably might not be able to see it. But this is the diameter of the Earth's orbit right here, and this is a 3 million mass black hole. Up here, this is a 200 million million solar mass black hole, and you can see that's the radius, or the diameter of this is actually bigger than the Earth's orbit. So the escape velocity is bigger than the Earth's orbit for things that are really massive. Okay, so in general, that's the basics of black holes. That's super basic, just giving you a brief overview. So if we look at our own galaxy is something called a spiral. So there are two main types of galaxies in the universe. There are spiral galaxies that look like pinwheels, and then there are just kind of blob galaxies, just kind of balls of stars that we call elliptical galaxies. So our galaxy is actually a spiral galaxy. So if you go out at night into a really dark area, you could see something like this. You should be able to see like a hazy band in the sky with like a dark kind of line cutting through it. That's dust and gas in our own galaxy. Okay, so this is an all-sky view of our own galaxy. And so what you can see is that there's like kind of an orange ball in the center. That's the central core of our galaxy. And then the other parts that you're seeing on the edges there, that kind of blue light, those are the arms of our galaxy. That's the spiral arms of our galaxy, just seen edge on. Okay, so our own galaxy has about 200 billion stars in it. And it's actually about 200,000 light years across. There's some back and forth about the actual size of it, but I think people are leaning towards 200,000 light years across. So to give you a sense of how big that is, so 200,000 light years, I mean, we throw around big numbers in astronomy, but you don't really get a sense of how big that really is. So to give you a sense, this is the light travel time of a beam of light from the Earth to the moon. Okay, so from the surface of the Earth to the surface of the moon takes about 1.25 seconds. So it seems pretty fast, right? But the distances are still pretty big between the Earth and the moon. This is the nearest object to us, right? So you can see that there's a lag between when a light beam leaves the Earth and when it actually gets to the moon, right? So a planet that's near to us is Mars, all right? So everybody knows that, there's Earth, then there's Mars is the next furthest planet out. The closest approach of Mars is about 3 light minutes away from Earth. Okay, so this is actually a beam of light leaving the Earth and getting to a really close planet to the Earth in our own solar system. This is how long it takes light to actually reach Mars. We're not going to watch this entire thing. But just to give you a sense of the vast distances, even within our own solar system. All right, so this is 3 light minutes. Now you have to imagine 200,000 light years, right? It takes light a very long time to go from one side of the galaxy to the other. So galaxies are enormous. And these black holes that we find in the centers of galaxies, we find these in the centers of almost every single galaxy we look at. They're very, very tiny compared to the overall size of a galaxy, even though they're hundreds of millions of times the mass of the sun. Okay, so what we know is, like, our own Milky Way has a supermassive black hole in the center of our galaxy. And the reason why we know that is because we can actually track stars orbiting around an unseen object in the center of our galaxy. And so the image on the right actually shows you the orbits of these stars, and the image on the left is tracing out the orbits of these stars around an unseen object, which is marked by that star, that white star in the center. And the image on the right is actually kind of raw data, a time lapse of raw data of these stars orbiting around an unseen object. And so by tracing out these orbits, we're able to estimate the mass that they're orbiting around. So by watching the Earth's orbit around the sun, we can actually measure the mass of the sun itself by doing that. And so what we find is that the mass that these stars are orbiting around is about 4 million times the mass of the sun, but it's in a space that's only 17 times the diameter of the sun. Okay, so it's actually a lot of mass in a very, very tiny volume. And the only thing that can be is a supermassive black hole. It can't be anything else. So we know in our own galaxy there's a supermassive black hole. And when we look at other galaxies, we actually see the same thing. We see that every single galaxy, essentially, that we look at has a supermassive black hole in the nucleus. Okay, so this is to give you a sense of how big a 17 billion solar mass black hole is. And so in the center there, that blue circle you're seeing is Neptune's orbit, so the furthest planet from the sun. And you can see the event horizon for a 17 billion solar mass black hole is enormous. Okay, this is actually tagged to a galaxy, but this has since been refuted. This is not accurate for this galaxy anymore. But this is just to give you a sense of how big these black holes can actually get. Okay, so probably the most famous black hole that you may have heard about is in a pretty boring-looking galaxy called M87. This is an elliptical galaxy. So this is one of these galaxies that's just a big ball of stars, no real features to it. Except on this one, you see that blue line coming out of it. And this is a jet of energetic material shooting out from the center of this galaxy. And this is actually coming from the supermassive black hole in the center of the galaxy. So what we're going to do is we're going to zoom in on that. Okay, so here's the same picture on the left, and now here's a little bit of a zoomed-in picture on the right that kind of shows you the jet a little bit more. So there's an equal jet on the opposite side. So this is actually coming from like the north pole of the black hole, and there's one at the south pole, but it's directed away from us so you can't see it. So you only see the north pole one, for instance. So if we zoom in on that, so now we have to get into artist renditions. So this is what, if we zoom in closer to the actual very, very close to the center of the galaxy where the black hole is, this is what we should see. There's actually a dusty torus around the black hole in the very center that's hiding the black hole from us, that could be hiding the black hole from us. And then the jets are coming from that black hole. So if we zoom in on that, so the picture on the right there is looking inside the torus. So if you look in the background there, you can kind of see like a wall where you can't see the stars in the back. That's the torus. That's the edge of the torus. But if you look in there, there's a bunch of material spiraling into that black hole, and that material heats up and creates magnetic fields. Particles get trapped in that and shoot out along the poles of the black hole. And that's those jets that you're seeing. So this is what we think we're seeing there. So within the last year, astronomers have actually been able to take an image of that torus around that black hole. And so some of you may have seen this image in the news, that image on the right. This is actually the first detailed image, of the material right next to a supermassive black hole. And this is from this galaxy M87. And this is groundbreaking. Nobody's ever seen a black hole before, and this is what we're seeing. So the interesting thing is, from this, we can actually get the orientation of that disk that's where all the material is falling into that black hole. And so people have done simulations. And so if you look at that little panel there on the right, they're numbered 1, 2, 3, 4. So 1 is completely face-on, so if you're looking at that disk completely face-on, and 4 is almost completely edge-on. And so what we're looking at is about number 3 right there. So it's slightly, almost close to edge-on, but not totally. And so you can see it's much brighter on the bottom than it is on the top, and this is basically caused by the black hole. It's light effects from the gravitational bending of light from the black hole. And so we can actually get the orientation of the disk from that. Okay, so we now know that all galaxies have giant black holes in their nuclei, right? We've seen them in our own galaxy, we've seen them in other galaxies. But the thing is that we don't know how these giant black holes end up in the centers of galaxies. We see them very early in the universe. So basically, as soon as galaxies form, there seem to be these supermassive black holes in the centers of galaxies, and we have no idea how that happens. A couple of ideas. One is that maybe a bunch of these stellar mass black holes, so these black holes that form from stars, maybe they merge together really quickly and create a supermassive black hole. There are problems with that. Another idea is that maybe just giant gas clouds early in the universe in these galaxies just immediately collapse directly into a black hole without forming stars first. It's really not known. But one key to that is that maybe if we find this kind of in-between phase of black holes, that maybe that can shed some light on how these supermassive black holes form. So supermassive black holes range from millions to billions of times the mass of the sun. Stellar mass black holes range from hundreds to about 1,000 times the mass of the sun. We don't really see any black holes between their mass range, but we have found about a dozen candidates with maybe 2 confirmed. So the key is to find a bunch of these so that way we can actually fill in the gaps, to find out how black holes go from, from whatever origin point to supermassive, if we can find these intermediate mass black holes in galaxies to make sure, so that way we can kind of understand the evolutionary track. So what happened in these galaxies that they didn't form supermassive black holes, they got stalled. If we can understand that, then maybe we can understand how supermassive black holes form. Okay, so the key to this entire, I don't know if this is working or not. Oh, it's working, okay, sorry. So the key to this is this really kind of simple relationship that was found between how tightly wrapped spiral arms are in galaxies and the mass of the supermassive black hole in the center. So this is a really simple relationship. So what people have found is that the more tightly wrapped the arms are in spiral galaxies, the higher the mass of the supermassive black hole in the center. So it's a really easy way to estimate the mass of a black hole in the center of a galaxy. All you have to do is measure how tightly wrapped the arms are in a picture of a galaxy. And so this is where this is actually really significant because it saves a lot of time. It's really easy to do. You don't have to track individual stars. You can just measure the curvature of spiral arms. Okay, so most of the time when we measure this property, we find that most galaxies kind of lie in this range. So we find galaxies with arms that are tightly wound to, modestly wound, but not really, really open arms. So most galaxies have these supermassive black holes lying on this end of the line. So what we want to find is galaxies that lie down here at the bottom in that green circle. If we can find galaxies that have really open arms and that could correspond to intermediate mass black holes, if we find those are the ones we actually want to pay a lot of attention to. Okay, so this is where the Citizen Science Project comes in. So the basic idea was to use this relationship and just go through catalogs of images. So just go through, it says astronomers take all sky surveys of galaxies all the time. And so there's just tons of data available. So you can just go into catalogs and just pick out spiral galaxies and just measure their curvature. And so the idea is just to have people identify and trace out the spiral arms in galaxies. Because obviously, so this is an image of one of these spiral galaxies from a catalog. And you can see there's not a lot of contrast between where the arms are and where the arms aren't, right? So it's pretty difficult for a computer to do this automatically. But people are really good at seeing patterns. And so, actually, I don't know if you can see this on the screen because the contrast may not be great. I can see it on the screen back there. But you can see that you can get a faint sense for where the spiral arms are, right? And so computers have a hard time picking that out, but humans can see patterns really easily. So if you can see that pattern, all you have to do is trace out the pattern. And then what we do is we throw away the image and we just use your tracings. Okay, so the project, what it ended up being called a spiral graph. So if you're interested, you can go to this website. It's scistarter.org/spiral-graph. And if you want to participate or learn more about it, you can just go to that website and check it out. But it was built on the Zooniverse Project Builder web platform. So if you guys are into astronomy, maybe you've heard of Galaxy Zoo, which identified galaxies maybe 10 years ago or something like that. It's still running now, but it started about 10 years ago. Zooniverse was built out of Galaxy Zoo, which is a really popular citizen science project. But again, the project that I built, Spiral Graph, wasn't really built by professionals. I mean, other than myself, it was built by volunteers and interns. So it was built by citizen scientists themselves. So some of the things that we're doing is, first of all, we take these images of galaxies, but we have to make sure that all the images we're looking at are actually spiral galaxies. So we ask people, is this a non-interacting spiral galaxy, or is this something else? Is this an elliptical? Is it a spiral galaxy merging with something else? So we have to make sure that people are actually looking at individual spiral galaxies. So we ask them, is it smooth or merging? If it is, it look like something on the left. If it's a structured and not merging galaxy, so if it's a non-interacting spiral, it would look something like the one on the right, right? And if they pick the one on the right, then the next thing they're asked to do is just trace out the spiral structure you see. And so this is just a little GIF showing a volunteer tracing out one spiral arm in a galaxy, right? And so we just have people just trace out the structure you see. And so this is an example of a completed galaxy. So on the left is the spiral galaxy. In the middle, you see the tracings overlaid on top of the spiral galaxy, and then we throw away the image and just keep the tracings. And so there you can see, obviously, the contrast between the background and where the arms are, right? So this is actually what we want to keep. And then what we do is we end up measuring the tracings. Okay, but we don't measure everybody's individual tracing. We get a bunch of volunteers to look at the same thing, trace them all together, and then we kind of aggregate that together to see where people agree. And so, again, this is that first image I showed you where the contrast wasn't great, but with 15 people independently tracing this galaxy, you can totally see where the spiral structure is. And from that, we're able to measure the curvature of these arms and then determine the black hole mass of this galaxy. All right, so what does this mean? It's a really simple project. Anyone can do it. I would say middle schoolers to anybody older. I would say, and basically it's what it's going to do is it's going to provide estimates of spiral structure. It's going to measure the arm winding of spiral galaxies, and hopefully find a bunch of intermediate mass black hole galaxies. I mean, if we come up with a dozen, that would be something. That would already that would already double the number of candidates that we've ever found. So, and then what the goal is if with all these candidates that we find, now we want to follow that up with actual observations to confirm that the black hole mass is actually in the intermediate mass range. And if they are, then we want to dig into what's going on with these galaxies. Why didn't they form supermassive black holes? What stalled the formation? And then hopefully understand how supermassive black holes actually get to their size. The other cool things that can come out of this, you can get different parameters for galaxies from the spiral structure as well. One of the main things, though, is that you can figure out how much dark matter is in a galaxy from this. So the winding of the spiral arms actually relates to the amount of dark matter, too. So the tighter the arms, there's actually more dark matter. The mass of dark matter in a galaxy is actually pretty high, too. So that's kind of interesting. But the really cool thing, I think, is that now that we have a bunch of people tracing out spiral arms in galaxies where it's really hard to see the spiral arms, we can create machine learning programs. So we can create artificial intelligence programs using this data as a training set for artificial intelligence. So hopefully, if we get enough people doing this, we may not need people to do it anymore, and the computer can do it for us. And so that's another goal that we're trying to do. So that way we can automate this entire process. We won't need people to do it anymore. We can do it much faster. But the problem is people are really good at this. It's just getting people to do it is the problem. So, and that's basically where I'm going to leave it. So if you're interested in spiralgraph, you can just go to that website. And if you guys have questions about galaxies, black holes, anything in astronomy, let me know.
Let's give Patrick a round of applause. Thank you. If you've got questions, wave at me. If you're down here on the first floor, I'll bring you a microphone because we want everyone in the room to be able to hear. If you're up on the second or third floors, just wave down at me if you have a question, and then you can yell at us, and we'll use our microphones to repeat the questions. Again, making sure that everybody can hear. So wave at me if you've got one and want to get us started, but I'm curious.
Yeah.
What's the critical mass of observations that you need to what's the critical mass what's the critical mass of observations that you need to call a galaxy settled, or to know what size galaxy you have? 15, 100?
Well, yeah, that's actually a tricky question. I'm using the Zooniverse model, in that they recommend, I think, between 10 and 20 observations before you call it done. So I picked 15, just because, I mean, if you use too few, the issue is that a lot of tracings don't overlap. People do kind of random things in tracing galaxies and things like that. I mean, you're asking about the actual tracing process, right? Yeah. So yeah, the issue is that people tend to do things similarly, but then there are outliers, right? And so you want to account for those outliers. So obviously, the more people you can get tracing an individual galaxy, the better your statistics are. The problem is there's a trade-off between collecting a bunch of data. There's a trade-off between how much data is necessary and how much time you want to spend on it. And I'm already finding that getting 15 people to trace an individual galaxy with a sample of 1,000 takes an extremely long time. So I'm actually thinking about dropping that down to maybe a smaller number where the retirement age for each object is slightly less. But for this first batch of 1,000, I actually have 6,000 galaxies I'm trying to get through in my first complete sample. And I'm doing them in batches of 1,000. And the first 1,000 is taking a while, but I think I'm going to keep it at 15, but maybe the next batch I might drop the retirement number down a little bit. But yeah, I mean, obviously the more tracings we have, if you have 100 people tracing an individual galaxy, the statistics are going to be great. But, it's a trade-off between, how much time do you want to spend on it and how good do you want the data to be. So you got to kind of balance that equally. So, yeah.
So everybody needs to jump on spiralgraph and get started.
Yes. We get it done so quick.
Yeah, you mentioned that some of these black holes are from the early days of the universe.
Yes.
How do we determine the age of a black hole?
Well, you can't determine the age of a black hole, but we can see black holes in the early universe, and we can determine their mass in the early universe. So some of the brightest objects in the universe are these things called quasars, which are the nuclei of galaxies very early in the universe that are extraordinarily bright. So when people first saw these, they thought they were stars, just really, really dim stars. But then they found out that these are actually galaxies, and that they're extremely far away. So if they were put right next to us, they would be the brightest objects ever. So we see these, and we see these objects, and the only thing that can be powering them is supermassive black holes, and probably we're looking straight down those jets directly at that. So it makes it super bright. So we see these supermassive black holes early in the universe. So and these are, and there's not much time between, when these galaxies form and when these quasars are seen. And so getting let's say a stellar mass black hole or a bunch of stellar mass black holes into a supermassive black hole in that short amount of time, dynamically is a problem. Mm-hmm. So, I mean, because we know the age of the universe, we know when we see quasars, we know when galaxies form, essentially. So yeah, we have time restrictions, and we need to be able to figure out how things behave in that time, so that way we can cram it in there, so that way it makes sense.
Mm-hmm.
Yeah.
All right, thank you.
Yeah.
We've got a question online. Is there a correlation between the number of stars / amount of luminous matter and the size of the central black hole? Number of stars and the size.
Yeah, so there's a correlation between essentially the scattering of stars in the bulge of a galaxy. So the larger the bulge of a galaxy is, the bigger the mass of the black hole in the center is. So we see that correlation. That's actually a really well-known, established correlation. So if we're able to measure the basically the size or the mass of that bulge of the galaxy, so that central core of a galaxy where you see a bunch of stars, that actually correlates really, really well with the mass of the black hole in the nucleus that's found in the very, very center nuclear region of that giant bulge. Yeah.
So does the size of the galaxy depend on the size of a black hole?
Actually, we're finding no. I don't think there's a good relationship between how big a galaxy is and how big the black hole is, because we're finding really large, like supermassive black holes in the centers of very tiny galaxies. So it's weird. So we don't know. Again, that's one of the things we don't understand is like how that works. How do these what's actually forming these supermassive black holes is really unknown. So why does it happen in giant galaxies? Why does it happen in small galaxies? We don't know.
So once you pass the event horizon, nothing's getting out. It's trapped.
Right.
So are those jets being formed in the accretion disk right before you hit that line of no return, or what's going on there?
Yeah, so I didn't get into a lot of detail with that, but what's happening is, so those jets, they're not part of that black hole. They're actually part of the accretion disk itself. So what's happening is, there's that accretion disk is just like dust and gas spiraling into the black hole, right? And so when it's on the outer parts, it's not rotating very fast, but as it gets closer and closer in, it's moving faster and faster. It's spiraling in faster and faster. And so it's rubbing up against the stuff that's further out. And so the stuff on the inner track is rubbing up against the stuff on the outer track, and it's moving faster, so you get friction out of that, so you get heat, right? And so when that happens, the gas will ionize, so it'll turn into like protons and electrons, which are charged particles. And when you get charged particles moving, you get magnetic fields. And when they're moving in kind of a pattern, then you get those kind of the magnetic field lines forming kind of around the black hole, which are perpendicular to the plane of the disk, which creates the jets along the poles. So it just centers on the black hole right there where most of the energy is going to be. And so it creates those jets. So those particles get trapped in those magnetic fields and get shot out. And that's what you end up seeing.
Let's go to the second floor for the next one.
Oh, so let me clarify. So if you don't have a disk, you won't see jets, and you basically won't be able to see a black hole at all, other than like the stars orbiting around it, like in our own galaxy. Yeah, sorry. Okay, yeah, no problem.
So you mentioned that you can, from the tightness of the winding of the arms, you can work out the mass of the black hole.
Right.
And you also mentioned that you can, it informs at least the amount of dark matter in the galaxy. To what degree? That sounds to me like two unknowns from one equation, two unknowns. How do you separate those? Yeah.
Well, these relationships have been determined kind of independently. So like the mass, so the winding and the mass of the black hole, for instance, what people have done is they've measured the mass of the black hole using other methods, right? So like the bulge relationship, the scattering of stars, for instance, things like that. So they've determined the mass of the black holes through independent means, and then they've just measured the spiral arm winding, and so they have an independent mass measurement, a spiral winding measurement, and they just plotted those, and they saw, oh, it falls on this line. And with the dark matter content, that's similarly done, in that it was determined in an independent way. It measured the spiral arm winding and saw it seems to lie on this correlation.
So if I could really quick have a follow-up question.
Yeah.
So it sounds like then that if both dark matter and the mass of the black hole have the same correlation to the winding, then they tend to be proportional to each other too. They directly.
It seems to be, but it's not known how they could be directly related to each other.
Yeah, that's interesting.
Because when you're talking about like supermassive black holes, you're really talking about on a relatively tiny scale, whereas dark matter is this giant pool that the galaxy sits in, right? So this is, so the supermassive black hole is, let's say at most 27 light days across, right? The galaxy, let's say our galaxy, is 200,000 light years across. The dark matter halo, like the dark matter content, right? That's like, much bigger than the galaxy. I don't even want to guess at how big that is, but it's obviously much bigger than the galaxy because it's a giant pool that this galaxy is sitting in the center. So, I mean, there's a correlation. It doesn't necessarily mean there's a causation.
Sure.
Yeah. So I don't know.
Thank you.
Yeah. So the question is, he was wondering if black holes can grow, and the answer is yes. So if material is falling onto a black hole, you're adding mass to it, right? And so like I showed in that equation. Sorry for the equation, but as if you increase the mass, right, the event horizon, the radius of the event horizon goes up. So if you keep dumping mass into it, the event horizon is just going to get bigger and bigger. So if you could take mass out of it, the event horizon would go down. But there's an idea of how to get mass out of it, but it's not really good. I mean, you're not going to be able to measure that at all. But yeah, you can dump mass into it, and it'll definitely get bigger.
All right, any others? Last chance. Yes, go.
You can have black holes merging with each other and then creating a larger mass black hole. And so we've actually measured that. And so I don't know if you know, there's an experiment called LIGO, this gravitational wave detector. And so what they were able to measure was two very compact, massive objects spiraling into each other and merging, and it creates this kind of ringing effect actually in space-time, like in space. So there's actually ripples in space that they were able to measure from the merging of two compact objects. And I'm pretty sure they measured two black holes merging. I know they got like a neutron star or two neutron stars merging. I'm pretty sure they got two black holes merging as well. And so that's actually remarkable. That experiment's remarkable too. So they were actually able to measure two black holes coalescing into a larger mass black hole. So that'll happen, yeah. So you can see that. I mean, in a way, you can see that, yes.
But we don't know of anything that can take out a black hole.
No, once a black hole's there, that's it. You have a black hole. Like, you can't get rid of it, really.
All right. This will be the final question. Last row.
So in reference to your research, how have you been getting the word out for people to do it? Yeah.
Well, I've been giving talks. I presented at conferences. I'm trying to gather volunteers at the museum. I'm just trying to talk to anybody who might be interested in it. I tweet about it, social media, things like that. I'm trying to get it as an official project on Zooniverse, and that already has like an automatic population of people who are interested in citizen science projects who volunteer to do that. So once it's an official project there, then you have an automatic audience. It's on SciStarter, which has an audience already. So I've gotten some people out of that. But yeah, it's just a matter of, just finding the people who are really interested in it and really don't mind like looking at, images of galaxies and tracing out structure that they see. So, and then, keeping them involved with it as well. So, because I mean, like people lose interest in things, right? I mean, people think it's really cool. They'll do it for a while and they just forget about it, and that's it, right? So it's kind of it's an ongoing process. I'm learning about marketing. I'm learning about all these things that I've never thought about before. It's almost like a business in a way. So yeah, so I don't know. I mean, I'm learning as I'm going, but we're getting there. We're we've already got like 8,000 classifications on this project. So I mean, there's a ton to go, but it's a pretty easy project. It's not it doesn't take a lot of work to do it. Like anybody can do it, and it's just a matter of keeping people motivated and recruiting new people for the people who drop out and things like that. So yeah.
I suggest a pizza party.
Yeah.
Let's give Patrick one more round of applause.
Thanks.
Thanks, Patrick.
Thank you.
And thanks, everybody, for coming out to the museum today. Thanks for sitting through the Lunchtime Discovery. It was a great time. Hope you learned something new. And hey, we'll be back here next Wednesday at noon. Bye, everybody.